All right, let's dive right into this explainer with a look at the ultimate all-time cosmic race, light versus sound. We're talking about a fundamental face-off between two physical phenomena that literally shape how we experience the universe around us.
So, you're watching a storm, right? You see this brilliant flash of lightning instantly. But then you wait. The booming thunder takes a few seconds to finally hit your ears. Have you ever wondered why thunder always seems to arrive so incredibly late to the party? Section 1. The lightning and thunder split. This everyday delay happens because a bolt of lightning rapidly superheats the air along its path, causing it to expand, well, violently. And that rapid expansion, that's exactly what creates the booming sound of thunder. But the light from the flash hits your eyes way, way before the physical sound wave can actually travel across the distance to get to you. To really get why this split happens, we need to break down the fundamental mechanics of these two very different types of waves. Section 2. Two very different waves. Okay, so sound is a mechanical wave. Think about hitting a drum. It generates a compression wave in the air, basically relying on molecules squishing together and pulling apart. Just like with that drum, sound absolutely requires a physical medium, whether that's air, water, or even steel, to actually travel. The particles literally have to physically bump into one another in a chain reaction to pass that kinetic energy along. And here's where the massive divide happens. Mechanical sound waves are totally desperate for particles to interact with. Without them, they're dead in the water. But then you have light. Light is an electromagnetic wave made up of oscillating electric and magnetic fields. Because it's a disturbance of fields rather than physical matter, light just doesn't need a medium at all. In fact, it thrives and travels perfectly well right through the absolute, total emptiness of a vacuum. Section 3. Comparing the cosmic speeds. Let's see how this whole mechanical difference translates into raw numbers, starting with the speed of sound. In dry air at about 20 degrees Celsius, it clocks in at roughly 343 meters per second. That's around 767 miles per hour. So yeah, it's fast, for sure. And we feel it all the time in our daily lives, like when a jet roars overhead. Now, contrast that with the speed of light in a vacuum, which hits a staggering physics-defining 300 million meters per second. We're talking roughly 186,000 miles per second here. This fundamental constant isn't just a big number. It sets the absolute unbreakable speed limit of the entire universe, a concept rooted right at the heart of Einstein's theory of relativity. So here is the crucial takeaway. Light travels nearly 1,000,000 times faster than sound in the air around us. And this massive million-fold disparity, it isn't just about why thunder lags behind lightning during a storm. It's the exact reason why our telescopes let us observe incredibly distant celestial events, basically in real time, visually speaking. Any sound from those events would take a ridiculous, totally impractical amount of time to reach us. Well, actually, scratch that. It wouldn't reach us at all, because as we just covered, sound can't even cross the vacuum of space. Section 4. How mediums change speeds. But here's the thing. These speeds aren't always set in stone. Sound behaves very differently depending on what it's actually traveling through. Because it relies on transferring kinetic energy between particles, sound actually travels significantly faster in denser, highly elastic materials. Just look at steel. Sound rips through solid steel at 5,940 meters per second. Compare that to a measly 330 meters per second in freezing air. Those tightly packed molecules in a solid just transmit the vibrations way, way more efficiently. Light, however, does the exact opposite. It's wild. The refractive index explains how light actually slows down when it hits dense materials. Things like glass or water. Because the electromagnetic waves are suddenly forced to interact with all these particles of matter, their overall transmission speed actually drops. For example, light's speed plunges by about 33% just by traveling through a pane of glass. Section 5. Can sound ever beat light? Which brings us to this absolutely fascinating hypothetical that actually sparked a huge discussion on a Reddit physics thread. If light slows down in matter while sound speeds up, can sound ever actually beat light? To figure this out, we have to look at these really incredible experiments where scientists pass light through a sort of slush of ultra-cold sodium compounds just to see what happens. Basically, they're creating a specially engineered, insanely dense optical medium. And inside this very specific medium, physicists managed to drastically slow the photons down to around 60 kilometers per second. Now, okay, 60 kilometers a second is still incredibly fast, but it begs a massive question. If you were to send a physical kinetic wave through that exact same medium, could it outpace the light? I just love how a Reddit user named Florin Andre perfectly explained this whole dynamic. They said, the speed of light in materials is like the speed of a group of runners through a forest. They get slower because they're dodging trees, but the runners do not lose their athletic skills simply because they are in a forest. It's such a great way to picture it, isn't it?
And this brilliantly illustrates the big twist of this whole explainer. Yes, a physical object, say a hypersonic bullet or a specific kinetic wave, could technically outpace the local transmission speed of light inside that specifically engineered medium. It's very similar to the concept of Cherenkov radiation, actually. However, and this is a big however, Einstein's cosmic vacuum speed limit, that fundamental constant c, remains totally unbroken. The light wave hasn't fundamentally lost its top speed, it's just taking a lot longer to navigate through the dense forest of that specific medium.
So, as we wrap up this explainer, I want to leave you with this final thought. We know the fundamental speed of light in a vacuum is an absolute, totally immovable boundary for the universe. But as we've seen today, by manipulating the medium, the universe always has a few absolutely fascinating tricks up its sleeve. If we can engineer these little loopholes where kinetic energy locally beats light, what other cosmic boundaries are out there, just waiting to be bent?